Now the next property is the viscosity, and the viscosity, I think you had studied in the your intermediate, or maybe in the O and A levels as well, what is viscosity all about. But we will discuss here in a little bit more detail, and even in the later on chapter number 3 we will detailedly understand how we can classify the liquid as well, or the fluid as well, with the viscosity behavior, and different types of instrument, that how they calculate the viscosity of the liquid. So here the viscosity is nothing, it's actually a property of by which the liquid offers resistance to flow. I really want to describe this phenomena with the context of how the solid body experience friction when it is moving in a particular direction or over a particular surface. Let's suppose there is a ball which is flowing, or there is a car which is moving in a particular road, and the road is so smooth. So what are the factors that are very much important to understand? Like one, the motion, the movement of the car depends on two factors. One is the friction. Definitely greater the friction, more the engine need to work on in order to speed up the car. Okay, and the second is but again the friction is actually the force which is opposing the motion, and the second is the friction factor, which is totally depend upon the surface of the road. Okay, which is not a force actually, but it is a phenomena which resists the motion of the body over any particular surface. Okay, it's also a factor. So similarly, the viscosity is a factor which affect whether the liquid offer greater resistance or less resistance. And the drag force is the force, just like the friction force, which apply opposite to the direction of the motion and try to restrict the body from moving from one part to another part, or gaining velocity, or it is responsible for retardation. If the car engine gets stopped, automatically the car will cover certain distance, but as the friction force continuously applying on the car, its velocity gradually decreases and decreases in such a manner that it's come to zero mark. So on the other hand, if we are studying the motion of liquids, the drag force is the force which is opposing force of the liquid. Okay, maybe the liquid, or maybe the solid body is moving through the liquid. Okay, it's also opposed that as well. But viscosity is something which is related to the friction coefficient, as we have discussed. What is the friction coefficient? It depends upon the nature of the road. If the road is not very smooth, the friction factor is very much higher, which represent it will experience greater friction forces. On the other hand, if we see it in the liquids or in the fluids, if the viscosity is higher, the body will experience greater resistance, the drag force, and hardly move from one place to another place. And if the viscous fluid is moving, so it will require greater shear stress to move on. Okay, so I think you can easily understand that viscosity is nothing, is just a factor, and a very identical factor which is associated with different fluids. Like water has its own viscosity, then an identical viscosity, and it differs from all other fluids like ethyl alcohol, gases, and other liquids. Okay, so I think you can easily understand it. Now this is a simple diagram which you need to understand, because we are going to do some derivation types of work as well. Okay, now this is a diagram which previously we have discussed as well, that this is a bottom solid boundary, bottom solid surface, and there is an upper solid surface, and the liquid is confined by both these solid boundaries. Again, this solid surface is at a stationary condition. Let's suppose at time is equals to 0, a very initial point of the process. Okay, and this force is applying, this solid surface is applying force tangentially to the upper surface of the liquid, again which is responsible for shear stress, and shear stress is responsible for liquid to move on in the form of layers. Okay, so here at time t is equals to 0, let's suppose the solid surface is present here, and there is no velocity profile within the system. But when the solid surface start to move and the time start from t to t2, so what happened? Definitely the solid surface has some velocity, and the liquid layer, which is very adjacent to the solid surface, will attain the same velocity what the solid surface has. And on the other hand, this is a stationary solid surface, and the boundary layer, which is very much adjacent to this solid surface, will definitely retain its velocity to 0 mark. And between of that, all these layers, we will see a velocity gradient. If we draw the velocity profile, definitely this part has the highest velocity, and from layer to layer it is decreasing and decreasing and decreasing. Okay, so these are the factors which we have discussed in the previous lectures as well, but the new thing which need to understand while before derivation is that, let's suppose from T1 to T2 the solid surface cover a distance of dA. Okay, and on the behalf of that we can say that it will produce the strain of angle beta d beta, with angle d beta. Okay, let's suppose this is the x-axis, this is the y-axis, and the velocity profile can be calculated by this. Okay, I think we can discuss it in on the board as well, which is more understandable to you. Okay, let's suppose I have made this complete diagram, and you can understand here that this is the y-axis, this is the x-axis. The upper plate move in this direction. Definitely the force applied by the upper surface is from left to right side. Okay, due to which the liquid undergoes this type of velocity gradient. So what do I exactly mean by the velocity gradient? Let's suppose we can say here that the velocity u is a function of y. Okay, why I'm saying this? Because if we move from this part to that part, definitely it depends on the y component. Let's y is a variable which maybe this equals to this. If you need to know the velocity, what's going on in that part, so what you will do is definitely this height will become equals to y, and the total length, the distance between the two surfaces becomes L. So what you need to do is y divided by L multiplied by the maximum velocity. So you will get the respective layer which is distance of y velocity profile. Okay, let's suppose if you are saying that you need to know the velocity which is present in the boundary layer of the bottom surface. So y definitely becomes equals to 0, and you will get u is equals to 0 ultimately. And if you are saying that you need to know the velocity what it is present at the highest level, okay, so for that the y becomes equals to L, and this equation reduces into L divided by L and multiplied by V. So it's equals to becomes maximum velocity. So this equation is used, or you can utilize it in order to calculate or determine the velocity of any layer with distance of y from a stationary level, a stationary solid surface to a particular part. Okay, so from here, let's suppose what we have done is we start with the shear stress. What is shear stress? Shear stress is nothing, just force per unit area, or on the other hand we can say that shear stress is directly proportional to a strain. Consider this equation. So u is equals to y over L V, and we have differentiated with respect to y. So what we have done, what we will get is du over dy, which is so called as velocity gradient, and it becomes equals to v over L. This is velocity gradient. Okay, after this, let's consider that the solid surface cover a distance of dA. So we can say that dA actually equals to we say that S is equals to V into dt. So it becomes equals to V multiplied by dt, which is the basic equation of the distance. Now we consider the triangle which is present here. Okay, as we know that shear stress is directly proportional to strain, and we say that if the shear stress is applied here, definitely that much angle strain is definitely produced, and if the shear stress is greater, this angle definitely will be much greater. If the shear stress is not is lower in amount, definitely this angle don't have that much magnitude what it has in higher shear stress. So when we consider this angle, so we consider this triangle. Okay, this is the base, this is the perpendicular, and this is the hypotenuse. So we know that tangent d beta will be equals to perpendicular, and the perpendicular here is dA over base, and the base is equals to L, the length between two solid surfaces, which can be rearranged, as we know that dA is nothing, just a product of velocity and dt, so it becomes equals to V multiplied by dt over L. And it's also rearranged in a manner that tangent d beta over dt is equals to V over L. And again here what we know is V over L is exactly equals to velocity gradient. So a strain is directly proportional to a stress, and on the other hand a strain is almost becomes equals to velocity gradient. So we can simply say that the shear stress is directly proportional to the velocity gradient, or the strain rate. One more thing which I need to tell you is tangent d beta is nothing, just equivalent to d beta. Okay, later on I will describe it on the presentation, because I have done some work as well, but what you need to understand is all these things calculation are done in radian, not in degree form like 90 degrees or 20 degrees. It's all done in radian. Okay, so we can say that d beta over dt is equals to velocity gradient. Let's suppose I write here all the equation so you can easily understand. It is equals to du over dy, and here in the place of a strain you can write the shear stress is directly proportional to du over dy. But for the cases, if we are dealing with the liquids, definitely the shear stress is directly proportional to strain rate is the equation for the solids. For liquids, we will come and in the equation of shear stress and shear strain, we consider the Young modulus. But here the proportional constant is depend on viscosity. Okay, mu, and this is so called the viscosity of the fluid, and which shows that viscosity is equals to shear stress over velocity gradient. So through these equations we can analyze that if the viscosity is higher, greater shear stress is required in order to produce a certain velocity gradient. And if the viscosity is much lower, on the application of very minor shear stress, the velocity gradient become much higher. So again, viscosity is nothing if you correlate it with the friction factor and the friction force. You can easily understand what is the viscosity all about. Viscosity is not a force, it's actually a property of the liquid by virtue of which the liquid offers or resists the motion within the liquid frame.